Okay, what I want to show you in this next video is what I consider to be the most useful and likely of the log applications that we're going to use in this course. And that is to simplify equations and solve them. So here, for example, from our book is in section 2.5, number 58. And there we are asked to solve this equation, 5 to the power x is equal to 12. Now, I know that 5 raised to the power 1 is 5. I know that 5 raised to the power 2 is 25. And I can visualize a graph like this that goes through the point 0, 1 and 1, 5 and 2, 25, and somewhere in between x equals 1 and x equals 2 there has to be a place where y is equal to 5. So I'm looking for this number, which is probably a little closer to 1 than it is to 2. Whoever would raise 5 to any power to get 12? Well, you never know. So what we're going to do is use log properties to figure this out. We have 5 to the power x is equal to 12. What we're going to do is take the log of each side. So I'll use the natural log because that's my favorite. So I have the natural log of 5 to the power x is equal to the natural log of 12. Now, natural log of 12 is just a constant that I can use a calculator to figure out. Using the rule that we know for getting exponents out of there by taking the log of both sides, this gives me x times the log of 5 is equal to the log of 12. Okay, these guys are constants. So I'm going to divide both sides by log of 5. What's left over is log of 12 over log of 5. Now, this is not equal to the log of 12 over 5. That's not what the rule said. The log of a quotient is a difference of logs. This is a quotient of logs. And so we don't have any particular rule for this. We'll just use the calculator. Okay. Here's the calculator. So, what I need is the log of 12, close paren, divided by the log of 5. And I do get a number somewhere between 1 and 2. I'm going to store that number in x so that I can check this result. Now, what I do there is I press store and then a variable name x to put it in. Now if I say, yo, what's x? There it is. Okay, so what was the initial question? It was 5 raised to what power is 12? So 5 raised to this power is 12, just the way we want. Now, I said I was choosing to use the natural log, but the fact is that I could use log to any base. Let's do this problem again with log base 10. So now I'm going to put a common log on both sides. Okay, I bring down the exponent, so I have x times the common log of 5 is equal to the common log of 12, which means that x ought to be equal to the common log of 12 divided by the common log of 5. So let's check that out. Log of 12 divided by log of 5. And there we are with the same value that we already checked out before. Okay, so in principle, you have a choice of what you get to use here. On the other hand, sometimes the choice is given if you have a 10 or an e in the base, then you're going to use a log base 10 or a log base e. Here's a kind of problem that I particularly like. An equation with different bases. So this is problem number 2.5.62. And it says 2 raised to the power x plus 1 is equal to 6 raised to the power x minus 1. So, presumably there is some magical x out there such that if we put it in the exponent of an exponential base 2, we're going to get the same value as we would get if we put it this way into an exponential with the base 6. Another way of looking at this is we have the graph of base 2 to the x plus 1, base 6 to the x minus 1. These two graphs cross somewhere. Where's that? Okay, so I'm going to use the same method that I had before. I need to make these exponents pop out of there. I pop out that exponent by using a log on both sides. So I have the log of 2 to the x plus 1 equal to the log of 6 to the x minus 1. Now again, I am at liberty to choose any base log that I like. There's no reason to prefer natural log over log base 10. Okay, out comes the exponent. So I have x plus 1 times the log of 2 is equal to x minus 1 times the log of 6. Okay, well, this means that I have some algebra to do. So x times log of 2 plus log of 2, I'm distributing the x plus 1, is equal to x times log of 6 minus log of 6. Okay, now I have some constants and some things that are not constant. So I'm going to move everything that has x to the left side of the equation and everything that doesn't to the right side of the equation. And that gives me x times log 2 minus x times log of 6 is equal to negative log of 6 minus log of 2. Okay, I admit this is not pretty. I'm going to factor an x out of both terms on the left. So I have x is equal to log times log 2 minus log 6 is equal to this stuff on the left, or the right. So x is equal to negative 6 log of 6 minus log of 2 all over log of 2 minus log of 6. Now this is kind of ugly, but it goes into the calculator just fine. So I need to be pretty darn careful about my parentheses because I have such a unpleasant mess in a quotient here. So that's the end of the numerator divided by another set of parens, log 2 minus log 6. And another set of parens. And so the whole expression comes down to, I would probably round that down to 2.262. At any rate, I'm going to store it in x. Okay, now I need to look back at my original equation, which said 2 to the x plus 1. So 2 raised to x plus 1. Okay, and this is what x is. I get 9 something or other, and then 6 raised to the power x minus 1. Close paren and move my cursor, and there we are. So we have our solution. Now I made a little graph when I was talking about this before. So I want to do the graph in the calculator so you can see what I mean. Anytime that we have an equation, no matter what it might be, an equation with a left and a right side, and we want to solve that equation for the variable x, we can graph the left-hand side. So we'll make that y1 in the calculator. We graph the right-hand side, that's y2. Okay? And then if they intersect, where they're going to intersect is at the value that we found algebraically. So here's that algebraic value. I'm going to try to remember that 9.593, and in the meantime, the reason I say try to remember that is because when I start graphing, this x that I stored with the 2.262, that is going to be overwritten by the calculator, which is going to take values -10 to 10 or what have you, depending on how I zoom. So we should see an intersection at x equals approximately 2, y equals something between 9 and 10. Okay, so I have 2 raised to the x plus 1. And I have 6 raised to the x minus 1. Okay, so let's zoom standard on that. There's one exponential curve. There's another exponential curve. Now let's change this window so we can see what's going on a little better. Maybe from -2 out to 3, because I want to spread it out quite well. And then from -2 up to 12. So this should show me the intersection clearly and give me some white space all around it for a beautiful graph. So 2 to the x plus 1 moved to the left some from 2 to the x. Look at that. Okay, so we had 2.62 roughly. I'm going to trace to 2.x equals 2.62. And it was 2.262. Bam! There it is. Okay. Let's look for that intersection another way. Item 5. So, I want to move a bit to the left, and I'll keep that value for the second curve. And guess, no, I never guess. Okay, and there we are at the same values that we found after we did all the algebra and all the processing with the log. Okay, so now we understand what it looks like from more than one point of view. Goal 1. Okay, I think that will hold us for a while with this kind of problem. We'll be seeing plenty of others.